Welcome to the A2 library. In today's video, we are going to talk about parent functions and their transformations. So let's talk about some basic parent functions. The most basic parent function there is a constant function. The form of a constant function is something like y equals a constant. So for example, y equals 2, or y equals negative 5, and so on. A constant function is basically a line, a horizontal line, at that point. So let's say y equals 2 would go up 2 on the y-axis, and it's a horizontal line at y equals 2. That is a constant function. Y equals negative 5, we go down 5 and draw a horizontal line at y equals negative 5. The next parent function is linear. Linear are usually in form y equals mx plus b, where m is slope and b is y-intercept. For example, y equals x will be the most basic parent function there is. There are no transformations in it. And y equals x has a slope of 1, which means it goes up 1 over 1. And then the y-intercept is 0, which means it's going to pass through 0 and has a slope of y of 1. Next one is called quadratic. And a quadratic parent function will look like y equals x squared. Now y equals x squared is just a parabola with the vertex at the origin, and it looks something like that. Next one will be cubic, which will be y equals x cubed. And the graph of that looks like this. Right, passes through the origin, and it is symmetric with respect to the origin. Next two I wanted to mention was square root, which is y equals square root of x. And it looks like this. Notice the domain of this function is 0 to positive infinity, and the range is also 0 to positive infinity. And the last one I wanted to mention was a reciprocal. Which would have an equation y equals 1 over x. And in this function, we have a lot of things going on here. We have what's called a vertical asymptote. We also have a horizontal asymptote. Notice the value of x cannot be 0. Therefore, we have the vertical asymptote. Another thing to point out is the domain and range of this function, which is all real numbers except for 0 for both x and the y, for both domain and range. Domain and range cannot be 0. Now that we saw some parent functions, let's talk about how we can move them, how we can transform them. So the first way is to add or subtract the number to the outside of the function. So let's say I have some function f of x is equal to x squared plus 2. So as you see, the parent function in here is x squared, and that 2 is added to the outside of that function. That 2 is going to move the function either up or down. So what I would suggest is drawing yourself a regular parent function. So y equals x squared, or f of x equals x squared, will look like this. I'm going to take every point on that function, I'm going to move it up 2. Right, so my vertex is no longer here at 0. It is now going to be at positive 2, 1, 2. So this point is now going to be moved up here. I'm going to just sketch this function that's moved up too. Let's take a look at the next example here. I suggest maybe pausing this video for a minute, giving it a try, and then press play. Hopefully you had a chance to draw this, and as I said before, I think the best thing to do is to draw the parent function first. So y equals square root of x is my parent function. Now that function is going to be moved down 4 because that number is on the outside of my parent function. So that is going to go down 4 because of the negative. So if it's positive, it goes up. If it's negative, it goes down. So 1, 2, 3, 4 down. And I'm going to sketch the same function as I did before, just move down 4. The next transformation we'll talk about is the vertical transformation. We just spoke about how a function can go up and down. Now let's talk about how the function goes left and right. We have f of x is equal to x minus 2 squared. What is that going to do to our parent function? Well, this one's a little tricky because the sign on the inside is going to move it in the opposite direction of what you would think. So I'm looking at this, I see that it's on the inside of the function, so I know this is going to go either left or right. But because it's going left or right, the negative is going to move it to the right, and the positive is going to move it to the left. So it's going to be opposite of what I would think. I would think that the minus is going to move it to the left. But yeah, there's one thing to remember, is that it's going to move it in the opposite direction of what you would think. So just like before, I would suggest drawing yourself the parent function first, especially when you're dealing with multiple transformations. Drawing the parent function can really help you out. I'm going to take this function, I'm going to move it to the right 2, right? The negative means to the right 2. So I'm going to go 1, 2, I'm going to go to the right, and that is where that function will transform to. Okay, it goes from here 2 units to the right. Now try this example on your own. Okay, hopefully you had enough time to take a look at this example. And again, let's identify the parent function, which in this case it's x cubed. So my parent function would look like this. Now since I have the plus 3 on the inside of my parent function, that's going to move it to the left. So for example, my origin is going to move 1, 2, 3 to the left. I'm going to draw this function just 3 units to the left. Now let's combine both of those in this example. Again, I encourage you to pause this video and sketch a graph yourself. In this problem, we have 2 transformations happening at the same time. We have a number on the outside, which means it's going to go up because it's positive. We have a negative 3 on the inside of the function, which I would think that it goes to the left, but it does not. It goes to the right. It goes opposite of what I would think. Right? And we also notice that the parent function here is the square, therefore it's a parabola. So the first thing I will do is draw what a parabola would look like if I didn't have any transformations to it, which would look like this. Now I'm going to take that parabola, I'm going to move it up 2, and I'm going to move it to the right 3 units, which means the vertex of this function is going to move out here. And again, I'm just sketching, not doing a great drawing here, but a sketch of what this function will look like when it's transformed. The next type of transformation is called a reflection. It's almost like a mirror image. There are two types of reflections. One about the x-axis and the other one is about the y-axis. First, let's talk about the one about the x-axis. So let's say we just have some basic function h of x is equal to negative x squared. So again, the parent function here is x squared, which is a parabola. But there is that negative in front of it, in front of the function. That would reflect this y equals x squared. This is y equals x squared. The reflection about the x-axis, which means I'm going to take all of my function and just turn it upside down. And that is now y equals negative x squared. A reflection about the y-axis happens when the negative is on the inside of the function. So in general, if I had a function f of x and the x was negative on the inside of it, that would give me the reflection about the y-axis, not the x-axis as we saw in the previous example. A great example to use here would be a function of square root of x, but let's say we put a negative inside of it. Again, I said this was a reflection about the y-axis. So let's take a look at square root of x, which looks like this. This is y equals square root of x. H of x is equal to square root of negative x, which means the negative is on the inside. That's going to reflect it about the y-axis and make a mirror image over to the other side like this. On the same graph, let's take a look at how, it's called g of h, would look if the negative was on the outside of x. So again, the parent function is square root of x, which we have here in red. The negative on the outside of that function is going to transform it about the x-axis, which is this axis. We're going to transform it around that axis, which means it's going to be a mirror image around that axis. This example combines all three of those transformations we just spoke about into one problem. What we have here is a flip about the x-axis, a transformation left, and a transformation up. So as I said before, I would first draw a regular parent function, which again here is x squared, and then I would apply these transformations in any order you really like. I would start with moving this point, any arbitrary point on this function, 2 points to the left, right? And then 4 up, 1, 2, 3, 4, which means my vertex has to be here, at this new point, negative 2, 4. Now it's also reflected by the x-axis, which means it's upside down. Therefore, it has to be like this. One parent function that is very common, but I have not mentioned before, is the function of absolute value of x. The graph of that function looks like a V. Absolute value, which means it looks like a V. Now, this function is great to demonstrate the next transformation, which is stretching. Now, stretching happens when you have a constant in front of the function. So a constant multiplies a function. In this case, you would have some constant multiplying the absolute value of x. The higher the constant, the skinnier this function will get. The closer that constant is to 0, the wider this function will get. So, for example, if I had function 2 absolute value of x, and then another function 3 absolute value of x, and another one 4 absolute value of x. and I wanted to draw them all on the same graph. That 2, 3, and 4 is going to make it shrink towards the y-axis. So my first one might look something like this, which is this is 2 absolute value of x. This is just absolute value of x. The next one be even closer, 3 absolute value of x. And 4 absolute value of x, you get the idea, it will be even closer. Now if I wanted to make it wider, I would take that function and multiply it by a number between 0 and 1, so a fraction or a decimal that's closer to 0. So 1/2 absolute value of x, 1/3 absolute value of x, 1/4 absolute value of x. And as the lower that, the smaller that function, that fraction gets, the wider this function will be. So 1/2 would maybe look like this. 1/2 absolute value of x. 1/3 would be a little wider. 1/3 absolute value of x. 1/4 will be even more wide. Okay? Now, you can do that until you get to negatives, and then if you recall from before, a negative flips the function. We finally come to our last example, which combines everything we talked about today. Once again, I would encourage you to pause this video and take a look at this problem and try to solve it on your own. Now that you had a chance to do that, let's talk about everything that's going on in this function. Let's start with the negative on the outside. That is the flip around the x-axis. Before multiplying the parent function is going to make it shrink quite a bit actually. -1 on the inside of the absolute value is going to make it go right, and the +2 on the outside is going to make it go up. You see there's a lot going on here, which is why, again, I strongly suggest draw yourself the parent function first. This is what the parent function looks like. Now that you have a visual of what that parent function looks like, you can go ahead and apply transformations. So the first thing I would do is make it go to the right and up. So I'm going to make it go up 2, and I'm going to make it go 1 to the right. I know my vertex is now here. I also know that it's going to flip by the x-axis. So I know it's upside down. But I also know that I need to make it shrink. Since we're just sketching, we're not going to make it exact, but we do want to show that it's much thinner and skinnier, if you will, than what the original function was. So the original function was, or the parent function is absolute value of x, which is just a v. And this function here is the one after transformations. So I really hope you learned something in this video. Thank you very much for joining me, and like and subscribe, and hope to see you next time.